So last time we introduced this concept of, say, Dirac notation, right? And Dirac-Brown-Cass state as a matrix representation of this quantum state or Schrödinger equation. And today we will continue describing this notation and how this Dirac notation can help us to understand quantum mechanics in a more elegant and useful way. So we know the definition of Dirac-Cass state and Brown state. And let's just try to do some algebra. And this algebra actually is the same thing that we discussed earlier without using the Dirac notation. Okay, so but you will see in just a moment that it's really useful to adapt this Dirac notation. So this expansion theorem saying that this any arbitrary wave function or Schrödinger wave function could be expanded in terms of a complete eigenfunctions, complete linear combinations of a complete eigenfunctions. Remember that. So now we could rewrite this expansion theorem in terms of a Dirac notation, meaning any arbitrary Dirac-Cass state could be composed in terms of the linear combinations of complete set of eigenstates, which I call this little n as a Cass state. So this is the eigenstate. And this orthogonal normalization condition for this complete set of eigenstates is given by this Kronecker delta function delta mn. We already defined this in the product between the Dirac-Brown-Cass states previously, right? So this is nothing but the overlap integral between any two eigenfunctions, psi n, psi m, and we could just use Dirac notation and simplify this, say, inner product in terms of this kind of matrix product. Okay, so what is the coefficient Cnm? This coefficient, if you apply this orthogonal normalization condition, this is given by inner product between Dirac-Cass state psi and a Dirac-Brock state n, where n is the eigenstate. So let's just plug in this coefficient back to the expansion. Okay, so now you see this power of Dirac notation. So the Cn as an inner product between the Brock state n and a Cass state psi, which is this one. Okay, since this Cn is just a number, so I can move this number around. I can put it here or here, but I decided that I put it here. But if you compare this two sides of the equation, you will see immediately that this on the left-hand side is a Dirac-Cass state psi, but on the right-hand side, it is still a Dirac-Cass state psi. But in the middle, you have something extra, and so this something extra is this one, right? And as you can see very clearly, this on the left-hand side, this is the Dirac-Cass state psi. On the right-hand side, it should also be a Dirac-Cass state, which is psi, the same state, which leaves this object inside the blue box identity matrix, which is called unit operator or identity operator. Okay, so let me just illustrate this stuff. So what is this? So why is this stuff equals a unit operator or identity operator? What does it mean? Okay, so we need to go back to the definition of this Dirac-Brown-Cass state. So on the left-hand side of this operator, it is the Dirac-Cass state, right? So it is given by a column matrix, which is made of this value of this wave function start at the discrete x position. Remember that you discretize this wave function, and then you put the value of this wave function at that particular position as a matrix element of this column matrix, which is what? N by 1, right? This is N by 1. So what about this Dirac state? And, well, again, so this is the Dirac state, which is this guy, what is given by, again, psi 1 star x1 psi n star xn, which is 1 by n row matrix, right? So from your high school knowledge in mathematics, you know how to make this matrix product, right? So a matrix product between a column matrix n by 1 and a row matrix 1 by n, which is what? N by n matrix. So this stuff right here represents a matrix. It's not a number. It is a matrix made of n by n components. And what are these matrix elements of the n by n matrix? Well, it is given by this diagonal matrix element psi 1 star psi 1 up to psi n star psi n. But what is this? You know very well that this is nothing but 1, isn't that? And this is also 1. Of course, you need to divide it by the number of sides. Okay, so by normalization and orthogonal condition of any Schrodinger wave function, you know immediately that this n by n matrix, which is formed by this matrix product, shows non-zero elements along diagonal and 0 otherwise. And the matrix element along diagonal direction are made of just 1, number 1. So this is called unit operator. So just like number 1, this 1 carrying a hat represents unit operator, which gives you this trivial result. So this is the quantum mechanical operator, which is so-called unit operator. So this operator acting on any Dirac state gives you that state, the same state. It's just, this is analogous to the number 1. When you multiply any number by 1, you get the same number, x. So likewise, this unit operator, when acting on any arbitrary quantum state, it gives you that same state, psi. As a result, you can actually insert this unit operator any place you like. You could insert this blue box stuff right here on the left-hand side of this psi or on the right side of the psi. So because it doesn't matter. And the original Dirac cat state is still the same Dirac cat state. So this is like a transparent stuff that you can actually take it away or put it here anytime, any place you like. Okay, so this is the magic of the Dirac notation. And if you sum over this unit operator, you get 1. So of course, this you need to sum over this stuff. So, which means that when you sum over all this kind of matrix product over entire this eigenbasis, you actually get back to this unit operator 1. Great, so this is called unit operator or resolution of identity in different reference books. And then we could re-express this we could take advantage of this, and we could understand the difference between any arbitrary state and Schrödinger wave function or wave function in momentum space. So there is a tiny or very subtle difference between these two concepts, any arbitrary quantum states. So when you think about this arbitrary quantum state, you may think of this as a Schrödinger wave function, but it can also be a wave function in momentum space. Okay, so let's just look at this relation between any arbitrary quantum state in the Dirac notation. And you're familiar with Schrödinger wave function or momentum wave function. So these two concepts are not exactly the same, but they are closely related. So let's just use this expansion theorem in the Dirac notation to understand the subtle difference. So let me just repeat this expansion theorem. Cn is this coefficient, and you know that Cn squared is the probability of finding an observable at eigenstate. Okay, so we will take advantage of such an interpretation, and we will argue that this probability of finding an observable to be at eigenstate and the Cn squared can actually be any one of these two. The Cn squared could be either the Schrödinger wave function or this phi p squared can be either psi x squared or phi p squared. Okay, depending on how you actually take the measurement. So this actually differentiates any arbitrary quantum state from a realistic, say, a realization of such a abstract quantum state in real space or in K space. Okay, so this arbitrary quantum state could be projected onto the real space, and when that happens, it gives you the Schrödinger wave function, but it can also be mapped onto a K space, and this, in this case, this projection of this Dirac cat state psi onto this K space gives you precisely this momentum space wave function square. So we will come to this interpretation in just a second. So let's take a short break. 狄拉克的这个算符呢，在量子力学里面是蛮重要的一个简化的一个算符哈，帮我们可以做很多简化，同时也使我们对于这些不同的量子状态跟波函数有要更精确的理解哈。那我们等一下就来看这个关联，就是Dirac state 哈，狄拉克的这个量子态好这样的 notation， 它是一个完全抽象的一个概念啊。那它所描述的是某一个 Hamiltonian 的某一个量子态啊，那它未必是要在本真态。那这个 Dirac cat state 或 Bragg state， 它可以就是投影啊，可以用一种投影的方式啊，投影就是内积啊，投影的方式可以投影到时空间。那投影到时空间，它就是 Schrödinger 的波函数。如果投影到动量空间，那它就是动量空间的波函数。但是呢，这个 Dirac 的这个 state psi， 它永远就是它这个 state。好，那等于说这个 Dirac state 可以说就是一个，如果说用人来做比喻的话，就是你自己哈，你自己。那么我今天穿某一套的衣服呢，我就变成某一样的装扮。那我明天穿另外一套衣服，我变成另外一个人。但是你还是你，你还是你自己。你今天穿这样的衣服，人家会觉得你是某一种样貌的外貌。可是呢，你明天穿另外一套衣服呢，你又是另外一种样貌。但是你还是你自己。这个你自己就是这个 Dirac 的 这个算符的底下的这个 Dirac state。Dirac state 是一个抽象的量子状态的一个概念啊，那它可以被投影在时空间，就是 Schrödinger 的 wave function。如果在动量空间，就是 momentum space 的 wave function。但是呢，我们必须要区分，是这个穿这样 A 这样子的套装的你，跟 B 这样套装的你，还有你自己，这三个之间有什么关联？表面上还有本质上有什么不一样？我今天穿了第三套衣服 C 的套装，是不是变成第三个人了？你穿了 A 套装跟穿了 B 套装，是不是同一个人呢？看起来不是同一个人，但是事实上是同一个人，穿了不同的衣服。OK， 我们等一下就来看这个比喻。So first, this eigenbasis does not need to be discrete. It can be continuous, such as position eigenbasis. Position state is the eigenstate of the position operator. Remember that. So this position operator x, whether in a hat acting on this positioned Dirac state, gives you this eigenvalue x, which is a continuous variable in real space, times this x state. So we can consider this position operator x, where in a hat acting on this, gives you this eigenvalue equation, which is obvious, but something which is not obvious is this expansion theorem. Can be extended to this continuous eigenbasis, where you could consider this as an integral rather than sum over this eigenstate. In other words, the sum over n becomes integral over x when we take this continuous eigenbasis to be the eigenbasis of position operator. Okay, so the sum over n that I wrote down earlier becomes this integral over dx. So the expansion theorem now in the continuous eigenbasis is written in terms of the integral over dx with the coefficient cx times this Dirac state x. But what is C of x? Remember, C of x is nothing but inner product between Dirac state and eigenbasis, right? And in this case, the eigenbasis of position operator x, and this orthogonal and normalization for the x eigenstates is given by this Dirac delta function. Remember that. Okay, so let's just look at this interpretation of this coefficient C of x. You could use the same way to understand this square of this coefficient. C of x square represents the probability that a measurement of the position of the state psi gives you the value x. Isn't that right? So this c squared is a probability that you find a particle at position x, right? But what is this? What is this? Well, by definition, this is precisely square of your Schrödinger wave function. Exactly. Okay, so in the very early chapter, when we define the Schrödinger wave function, the square, the magnitude square of the Schrödinger wave function is the probability density that we find a particle at particular position x. And in the expansion theorem, the cx squared has exactly the same meaning of finding the particle, the probability of finding a particle at a given value x. As a result, we could really identify this two. This is something non-trivial. This is very important. So a Schrödinger wave function psi of x is nothing but the inner product between arbitrary quantum state psi and the position eigenstate x. And we call this inner product is the projection. You project this psi, this Dirac state, onto the position eigenbasis. And this projection gives you precisely the Schrödinger wave function. Okay? So you could actually do the same thing. You can imagine that this eigenbasis n could be not the position eigenbasis, but the eigenbasis of momentum operator. Suppose this little n with the Dirac notation represents the eigenstates of momentum operator. Okay, this p cat state is the eigenstate of momentum operator p, and then we could again apply the same expansion theorem to expand this any arbitrary quantum state psi in momentum eigenbasis, which means that this psi is actually C of p and state p. And then, of course, the C of p is defined as the inner product between, say, arbitrary Dirac state psi and this momentum eigenbasis p. Right? So if you square this, this is precisely the probability that you find a particle at the momentum state p. Right? This is momentum space wave function. So remember, in chapter 1 or chapter 2, we defined the momentum space wave function as a Fourier transformation of a Schrödinger wave function. Right? So here I can actually produce two different wave functions. One is the Schrödinger wave function. Another is the momentum space wave function phi of p by using the same Dirac state. Okay, so this is the key point, that you actually use the same Dirac state psi, and you could either project this psi onto the real space eigenbasis, and coefficients give you the Schrödinger wave function. And you can use the same Dirac state psi, but you project onto different bases, which is momentum operator eigenbasis. And in that case, this coefficient is precisely momentum space wave function. Of course, this psi of x and phi of p, they are related by a Fourier transformation, but both wave functions come from the same Dirac state. So this is my analogy that I mentioned a few minutes ago. So this is you, and on Monday you wear a suit, and this is you on Monday. And on Tuesday you wear another dress, and you look like phi of p, but this is you on Tuesday. Of course, superficially, you on Mondays looks differently from the person, which is you, wearing a different dress on Tuesday. But the key point is that you is you, right? The person wearing the suit on Monday is you, and the person wearing another dress on Tuesday is also you. Okay, so this brings a very important concept in quantum mechanics, namely a Dirac state is an abstract idea of a quantum state. So it has everything. It can be a Schrödinger wave function. It can be momentum space wave function, depending on which eigenbasis that you want this abstract quantum state to be mapped onto. Okay, so if you like to map onto, say, the real space, it will look like Schrödinger wave function. But in momentum space, if you project psi onto momentum space, it is phi of p, the momentum space wave function. But this psi, as an abstract idea of a quantum state, it has all the information of the Schrödinger wave function, also momentum space wave function. It is waiting for you to do the projection. But before the projection, it is an abstract, in a sense, it is very abstract idea of a quantum state before it is mapped onto any eigenbasis. It can be mapped onto any eigenbasis. So by using Dirac notation, you could really precisely understand what is the difference between any quantum states and a projection of that quantum state. Okay? So psi, of course, is different from any projection, but it can be projected onto any eigenstate or eigenbasis. But of course, this is very important. This psi as a Dirac state, it is neither Schrödinger wave function nor momentum space wave function. It is the quantum state before any projection. It has all the information you need to know once you perform such a projection. So this projection is really important and a key concept in quantum mechanics. Okay, so this is, I think, very important message that you should take home, meaning using Dirac notation, the idea of a quantum state could be projected onto any eigenbasis you like, and it has many representations depending on where you want this state be mapped onto. Okay, so let's just take a short break, and we'll come back. We will literally compare this kind of interpretation and the Dirac notation in a definition of Hermitian conjugate operation and all the previous defined identities. And of course, we will derive this plane wave solutions of a free particle to identify this wave function as Schrödinger wave function. So let's just play this unit operator and insert this unit operator at will, whenever we like and wherever I want. So there are two representations of such a unit operator. One is the discretized version, which is sum over this Dirac and Bragg state as a matrix product. Another is the continuous integration over X, as I mentioned. So if you can try to do this, play this trick onto this any, say, overlap between Dirac Bragg and Cat state that I just wrote here, and if you plug in this kind of a identity operator, and you'll see that this is nothing but overlap integral that we defined earlier. Okay, because this unit operator could be inserted any place I like. So I like to insert this unit operator in the middle between psi 1 psi 2, and I simply just plug in this definition, which is right. So I can simply just plug in wherever I want, whenever I like. Okay, so this unit operator 1 is given by this integral over the x, and inside the integrand it is the matrix product between this eigenstates of x operator, and this is by definition, and it is the integral like this. So now I could just look at this integral in a different way. So suppose I do not look at this yellow circle, but I look at this red circle right there. If I do this, and if I simply just use correct interpretation of this projection, remember this is projection, right? Between what? Psi, Bragg state, and x eigenstate, right? And this is another projection between psi 2 and x. What is this projection between psi 1 and x? Well, this is nothing but psi 1 star of x as a Schrödinger wave function. We just argue that they should be interpreted this way. And likewise, this is what? This is psi 2 of x by definition. As a result, this Dirac inner product is nothing but the overlap integral that we defined earlier, right? Okay. So of course, without using Dirac notation, you can also very well defined as overlap integral, but with the help of Dirac notation, this complicated integral reduces to this very elegant, simple notation like this. It is a projection between psi 2 as a Dirac cat state and psi 1 as a Dirac broad state. And in terms of a Schrodinger wave function, it is precisely the overlap integral between two Schrodinger wave functions. Okay, so you could generalize this kind of a definition of projection or inner product between Dirac broad and cat state phi and psi in the same way. Okay, so now you see the power of a Dirac notation, right? So you could simplify this overlap integral between two wave functions as simply just a projection between Dirac broad and cat state. Of course, you could project this kind of operation onto any arbitrary eigenbasis, not necessarily this position operator eigenbasis, but you could also project this onto momentum eigenbasis in such a way. So this is just an overlap between two momentum space wave functions. So you could insert any arbitrary eigenbasis you like. It doesn't need to be position eigenbasis. So let's just look at this term. The particle can only meaning it's more than to actually consider regarding this projection occupied at this one of this eigenstate, right? It cannot be at arbitrary state wave function. Is precisely what we defined earlier if we adapt this Dirac interpretation. Yeah, that's it for today.